that puts us where? That puts us roughly a week before spring break, I think? Okay, so at least we get to pretty well cover all of aromaticity before spring break. When we come back from spring break, we might have a chance to spend the week doing problems. And then we have what sounds like the first week in April for the topic 3 examination. There you go. All right. We're on schedule. We can afford a few more big blizzards and wouldn't hurt us too much. All right. But with regard to this material, the trick is going to be to make sure that you can keep this organized in your mind. The overriding theme for this latter half of topic 2 is somehow it involves carbanions, typically alpha carbanions. Okay? So if you can remember that, hopefully it'll enable you to keep this all under control. So here is this second half of the meat portion of this topic. Here we have what are called alkylation and acylation reactions. What does an alkylation reaction do?
Alkyl.
So we're going to attach an alkyl group to what had been an alpha carbanion carbon. If it's acylation, what we're doing is we're letting the alpha carbanion carbon attack a carbonyl carbon that has a decent leaving group. Typically an acid halide is good. And then we're going to talk about conjugate addition reactions, and it's better if I just let you see what that looks like when we get to it. So here we go. These go by names. Please don't let the names put you off. All right. The first one is known as the malonic ester synthesis. That name won't mean anything until you see the slide, and perhaps even then, might not mean that much. We also have the acetoacetic ester synthesis. And then we have what's known as the Stork enamine synthesis. Stork is a proper name for what it's worth. Gilbert Stork worked at Columbia University for most of his career, a little bit downtown of where I did my undergraduate work. And then we have a miscellaneous hodgepodge of what are called Michael addition and conjugate addition reactions. So again, you had 4 reactions last period: the aldol, the Claisen, the Rafamatsky, and the Wittig. Now you have yet another 4, so as long as you take them in small bites, hopefully they're digestible. So let's see what all this looks like. Yes, let's see. There we go. All right, so there you go. There's a self-explanatory slide. I don't need to explain anything, so we'll move on. All right, so what is this? What's going on here? All right, well, first of all, how about we address what the name is? It's malonic ester. Well, malonic ester is an ester derived from, guess what acid? Yeah. Does anybody know what malonic acid looks like? I'll give you a hint. It's the second of the dicarboxylic acids. Imagine sticking a CH2 right smack between 2 carboxyl groups. Can you picture that? So what you have is, I don't know why this particular portion of the board doesn't seem to take this marker. But anyhow, if there were hydroxyl groups attached to these carbonyls, that would be malonic acid. And what you're looking at is the use of what substance to replace that OH group? No, that's not what it is. That's an ethyl group, but I asked you what substance replaced the OH group. How'd you make this?
Ethanol?
Yeah. One used ethanol in order to replace the OH group, either directly if you wanted to use the brute force approach, or by first turning the acid into an acid halide and then kicking that out with ethanol. But the point is, malonic ester is the diethyl ester of malonic acid. That's what it is. All right? So you might be wondering, one, why, if we can get our hands on malonic acid, are we bothering with the ester, number one? And then, what's so special about it? Well, this is probably going to be the first of a number of starting materials that have a very special feature that we are going to take great advantage of, and that is the fact that this carbon and set of hydrogens happens to be not alpha to just one carbonyl group, but to both. Okay? And there's a technical term for that, because what we're going to do is, as you see here, we are going to take advantage of the presence of two adjacent pi systems, because when we create a carbanion, that negative charge can now be delocalized not over one pi system, but over two. As such, this is not your ordinary run-of-the-mill alpha carbanion. The technical term that I was alluding to is, this is a sandwich alpha carbanion. A technical term that I made up. Okay. But it does the job. So these sandwich carbanions are even more stable than just your ordinary mono alpha carbanion. So the question is, you've made it. What can you do with it? Well, it turns out that this is a wonderful nucleophile. Okay? And in what kind of mechanism is it desirable to have a wonderful nucleophile?
SN2.
SN2. And as soon as you say SN2, that nucleophile had better not be attacking anything crowded, which means that you're unfortunately limited to attacking only methyl and primary halides. Secondary is not permissible. Tertiary is totally out of the question. Right? So here is what happens. The SN2 reaction takes place. I've succeeded in creating, as the theme of this topic is all about, making bigger and better carbon skeletons. Well, it's not that bigger, but it's bigger. And notice, although I don't have room in this slide to show you all this, at the risk of confusing you any more than I have to, I still have an other alpha hydrogen here. If I wanted to, I could just subject this product to more of the strong base. Notice that the strong base is the conjugate base of the very solvent that also constitutes the nature of the ester, ethyl ester. So this way, if this material that I want to be ripping off hydrogens chooses to attack the carbonyl and kick that out, would you ever notice? No. So that's why we're using what we're using. But the point is, I can use it again to rip off that hydrogen. And it's up to you now, depending on your need. You can attack the very same thing again and put two of these carbon groups on this alpha carbon. Or you could have chosen something entirely different from that. Again, as long as it was uncrowded, that would work. And you'd have two different alkyl groups up there. All right? So you've got your alkyl groups attached. What now? Now, the rest of this is strictly one option out of many, but it's one that's frequently used, so I thought I would illustrate that. And again, I apologize for the poor quality of these things. I don't know what's happening. Is it possible for these things to simply deteriorate over time on these discs? No? Really? I think given enough time, this is all going to disappear. And in case you haven't been reading the news, those of you that save your photographic, in quotes, memories on disk, you better take other measures. Start snapping real pictures. Okay. In any event.
Why is that? Sorry.
Because the kind of saving that people are doing with their, in quotes, photographs is all bits. Yeah. Zeros and ones. That's it. That's not going to last forever. Hell, I might outlast it. Okay? So it's all going to disappear. When they say the cloud, they really mean it. It's just going to disappear.
1 meter solar flare.
Yeah. You take my word for it. You heard it here first. Okay. All right. So, in any event, what we can do is, one, we can subject our diester to acidic, or for that matter, basic hydrolysis, and turn it back into the diacid. And if I did this on the basic conditions, I'd have to acidify the medium to turn the disalt into the diacid. But why is something like this of any interest to us? And the answer is, if you can remember your acid chemistry, this is not just any old diacid. This is a geminal diacid, which means that if one took it into their head and you subjected it to strong heat, not dehydrate, try again. You had the right beginning. You can what?
Deprotonate.
What am I getting rid of?
CO2.
What's the name for that process? Decarboxylation. So that's it. And notice that when you look at this final product, what you're seeing is that from the original malonic ester, can you see what part is left? Just cover over one of these carbethoxy groups. You have all of that gone. And what took its place? Whatever alkyl halide you used in the alkylation process. And when you look at the combination of the two, notice, you can't see it too well here, but if you printed it out, I hope you can. This is in one color, and this is the alkyl group that you put on. Well, what is that? If it's one hydrogen short of being what?
Propanoic acid?
Name the acid.
Propanoic acid?
How many carbons do you see?
Acetic acid.
Yeah, acetic acid.
I thought you said.
So in other words, all of this is just to replace one hydrogen of the methyl group of acetic acid with an alkyl group, and you can think of this as making substituted acetic acid. That's one option, but it's a very popular one. Okay, and you'll see how this is all utilized. So, do we have any major questions that we need to raise about this process? Because this story is going to be told in a number of variations, but it's the same story. Okay? So, I'm taking advantage of an alpha carbon position to 2 pi systems. That's going to allow me to create sandwich carbanions that I can now use as nucleophilic species to attach carbon skeletal pieces to my final product. So let's see what this looks like. Here is a very similar type of process. Same theme. I'm taking advantage of the greater acidity of these hydrogens attached to an sp3 carbon. Because of the presence of 2 pi networks, I generate my sandwich carbanion, and this time I use it not to attack a primary alkyl halide, but an acid halide. That's why the name of this is acylation and not alkylation. So what happens is the carbon attacks here, generate O minus regenerates the double bond, and out goes an electronegative atom bearing negative charge. And although you can't see it very well here, there is a bond connecting this to that alpha carbon. And what happens is that now, if you weren't interested in this as your final product, again, you can hydrolyze your ester. You've now got your geminal diacid. One of these 2 acid groups can go away. In fact, both of them can go away. Why can both all of a sudden go away when previously only one went away with strong heat? Anybody? Say again? Because I have a 3rd carbonyl group there. You don't have to have just acid groups on the same carbon. As long as you have 1 carbonyl group that's willing to remain behind, those that can generate CO2 are just going to disappear. And they chose to disappear. So I heat this thing strongly, and wham, bang, 1 CO2 molecule leaves behind its H. The other CO2 leaves behind its H, and this all of a sudden ends up being a methyl group. So the net result of this process then is that I create some kind of a methyl ketone. So if you have any need for making a methyl ketone, this would be one way in which it can be done. Is everybody following this? Yeah. It would be too much to ask if you could repeat this spontaneously, but as long as you're following it, we're in good shape. Okay, so just as I have these 2 options with the diethyl ester of malonic acid, alkylation versus acylation, there's an other starting material. It's a combination ketone and ester. Let me show it to you in the next slide. Here it is. That's my starting material. Okay. This is known as acetoacetic ester. Why is it called that? Well, first of all, that is the ethyl ester of acetic acid that I'm letting you see. And here is the aceto version of that name. So acetoacetic ester. Right? Why is this of any interest to us in lieu of the previous slides? What's this have in common?
A sandwiched.
It's going to be a source of sandwich carbanions, you betcha. Okay. And I like this one because it gives me an opportunity to ask the relevant question, I hope. Where the devil did you get your hands on that? Because I'm telling you that you're impoverished, you can't buy it, you have to make it. Using chemistry that we discussed last period. That's your hit. Okay? tell me how we got our hands on acetoacetic ester. Where did it come from? This is the test of how well you're understanding what we're talking about. I'll give you a hint. It's a beta keto ester. Yeah, Claisen. That's a start. Good. Okay. Look at that particular structure and ask yourself, because a Claisen comes in two varieties, self or crossed, is that the product of a self-Claisen or a cross-Claisen, do you think?
Say cross.
You think crossed?
I don't think so.
He thinks self, you think crossed. Well, we have to settle this.
I mean, they both.
So hang on. All right? Are you asking yourself the critical questions? As you look at this skeleton, where was it put together? By Claisen. Where? Where was the connection made?
On the carbonyl of the ester.
The carbonyl of the ester, right here?
Yeah.
Wrong. Afraid not. Ask yourself this. Which carbon in a prior life must have been the carbanion carbon?
One from
Oh, yeah.
The carbonyl carbon?
The other one.
What do we call that one? Give me a Greek letter.
Alpha.
Yeah, the alpha carbon, right. So, the question is, when it was negatively charged, did it attack that carbon and kick something out, or did it attack that carbon and kick something out? What kind of starting materials must be used in a Claisen?
Ester.
Esters, only esters. So, I see this ester, and that would be alpha to it, so I can have thought of that as an alpha carbanion in a prior life. Well, if that was the alpha carbanion, what ester was that?
Methyl ester.
Wrong. Why would you say that?
Well, I mean, if it. Unless it was the same thing.
You're damn right it was the same thing.
That's why it's so.
That's why it's a self-Claisen. So let's show you. Oh, man. Wait. There's more here. Let's see if this works any better. So how about this? Oh, that's much better. Okay. So watch this. Here is O-ethyl. And now imagine, if you will, here is the other molecule turned into the alpha carbanion. Can everybody picture this? These were once both the same molecule. That's why this is a self-Claisen. This attacked that carbonyl carbon, and without going through all the rigmarole, pi bond broken, O minus regenerates, C double bond O, out goes this. That's how the connection was made. That's how you got your hands on that. Okay, so it's very nice that we start with a Claisen before we actually get to use this reaction. This one is going to have the same theme as the previous one. I'm making a sandwich alpha carbanion. I'm choosing once again to do an alkylation first. I've done it. I still have an other hydrogen. If I desire to rip that one off, I can put either the same or a different alkyl group in place. But if I decide enough is enough, I'm now going to hydrolyze the ester, turn it into a carboxylic acid, and although this is not a geminal diacid, it doesn't have to be, in order to undergo decarboxylation because I still have a carbonyl group on that same carbon as my incipient CO2. If I now go ahead and heat the living daylights out of this thing, this is going to be lost as CO2. This H ends up over there. And voila. You've made a new entity via this so-called acetoacetic ester synthesis process. You okay? All right. It's a good thing it's going to be snowing all weekend. You have no place to go. You'll just occupy your time just looking over these slides until they become second nature to you. Okay. So, if I can get away with alkylating, and for the record, if you look over here, the summary says that this product can be thought of as an acetone molecule to which you've attached the alkyl group. So, if you find it useful to think of it that way, then by all means, you go ahead and do that. All right. If I can alkylate, I can acylate. So let's show you what that looks like. It starts off the same way. We've taken advantage of the alpha carbanion carbon sandwich between two carbonyls, turned it into the carbanion, but this time no more alkyl halide, this time acid halide. Carbon kicks out, leaving group runs off with sodium. Now I have this attached to this carbon, so that means I now have one ketone, a second ketone, but I still have this ester that can be hydrolyzed. Here I'm hydrolyzing it, despite what the slide doesn't show. And I've now got one acid group on a carbon that has more than one carbonyl group. So this is carbon dioxide waiting to happen as soon as I apply heat. I apply the heat, and now instead of having an alkyl group attached to that carbon of what would have been acetone, I have an acyl group. So I've got a beta diketone, which, by the way, this beta diketone, notice, it's got its own alpha carbon sandwich between two carbonyls. You could use this as a starting material and make up your own reaction. Apply your own name to it. Okay, so in any event, questions about these four very closely related types of reaction. They all involve some kind of sandwich alpha carbanion. If we're doing alkylation, then the reaction is SN2. If we're doing acylation, then we're attacking an acid halide. Okay. Let's show you this one. Now, this is not going to be a user-friendly slide, so I'll try and walk you through this. You know, it's funny. As I look at the slide on my screen, I can see all the bonds, so I am now beginning to think that it's not my fault. It's the fault of that projector.
Yeah, I mean, I can see all the bonds fine. Too.
Yeah. So, we're using scientific deduction here. If it's not us, it's got to be that, right?
Yeah. I wonder if we could focus it. I wonder if focusing would.
Focusing it.
I mean, I don't know if it would bring out the colors better. Or...
See, my approach to dealing with problems like that when it comes to instruments is I give it a good kick, and that either takes care of the problem or we get a new piece of equipment. One or the other.
You like the latter one.
Yeah. But in any event, what's going on here? This is really very elegant work. Let's see how much you remember. If, let's say, you have a carbonyl compound, and this one has the same restriction on it as the aldols and the clasins. There can only be one alpha hydrogen environment in my starting material. Just one. And you'll see why. So I'll just go along with, acetone, give you another example of something that would have just one alpha hydrogen environment. I could go with something simpler than a methyl group. This has only one alpha hydrogen environment. If you don't like any of those, you can go with benzene, no alpha hydrogen environment there. So any of these things has just that one set of alpha hydrogens. I'll go back to my acetone though. All right? And you tell me, if I treat this with NH3, I'll give you a hint. Okay, that was your hint. What does NH3 do with respect to the carbonyl group of acetone? And creates a double bond to N, and the N now can only have how many more bonds and be neutral? And what do you think is on there? H. Okay. Do we recall what we call this kind of product? This will come up again in topic 4, by the way. See, now you're going to have to spell things. Okay. A-M-I-N-E. Afraid not. This is ammonia, and you're going to see me say momentarily, what if I use instead of ammonia, which is not really organic, but if I have a carbon group attached to my nitrogen, just one, it would be what category you mean? Primary. Yeah. Okay, so the point is, this would be truly, for the purpose of emphasis, an amine. This, by contrast, is an imine. And you've already seen right here, where is it? See it? Now we have an enamine. And if you start saying these things rapidly, one after the other, you sound just as if you're talking baby talk. You'll see. Okay. So here is the story. If I have ammonia with 3 hydrogens to begin with, I'm going to lose 2 of them and the oxygen that creates a water molecule. Agreed? Okay. If I come along with a primary amine, I've still got 2 hydrogens and the oxygen to lose as water, so I can create an imine that looks like that. Still with me? These are imines. But what if I came along with an insufficient number of hydrogens on nitrogen? What if, instead of a primary amine, I come along with, would you believe, a secondary amine? So what happens now? So let's go through the mechanism here. All right. Here is NH. Here are 2 carbon groups. I'm going to have, and you can see it up there, I think. You can see that this thing attacked that, did that. What happens immediately thereafter? So let's show you. So here is O minus. Here is N with H. There's only one H. Hang on. There's only one H. And there are 2 R groups. and this is quaternary, and here is that other methyl. Okay. So here I have O minus, here I have hydrogen on positive nitrogen. There is going to be a transfer from one to the other. It doesn't have to be an intra, but it's the easiest way to think of it. Intramolecular proton transfer. So when that happens, I now have OH, no more positive charge because the nitrogen now has its lone pair back. But this is a geminal amine alcohol. And you can see that there's a name for those that I love to pronounce animal. Okay? So, just as a gem diol is going to spontaneously lose water, these aminols also would like to spontaneously lose water. But the problem is, unlike ammonia, unlike a primary amine, where there would have been that other hydrogen on the nitrogen to create the double bond here, there isn't, because you use the secondary amine. So this thing is still dying to lose water, so guess what it does? The OH is not going to lose a hydrogen from this because there isn't any. Is there a hydrogen next door to this carbon? There it is. So what happens is one of these goes along with the OH, and voila. So instead of getting an imine, you get a combination alkene amine, better known as an ene amine. And that's what this is. Okay? And as nice as it is to keep saying that over and over again, what is it really? What good is it? And what does it have to do with what we're talking about? Well, let's see if I can show you. This will probably be the last time you see enamine referred to again. All right, you ready? You can see that if I take this pair of electrons, push it here, that's going to push the pair of electrons from the so-called alkene onto this carbon. See it? What was this carbon originally? Go all the way back to the beginning. That was the carbonyl carbon. If that was the carbonyl carbon, this, then having a carbon with negative charge right next to it would create what?
Delocalization?
Say again, what?
Alpha.
An alpha carbanion. Sound familiar? Yeah. So in other words, all of this is being done, in essence, to create a disguised alpha carbanion. And once you have your alpha carbanion, guess what? You can do alkylations, you can do acylations. All right? So here, let me show you what was chosen. We're using the character of an alpha carbanion to attack in SN2 fashion a primary alkyl halide. This carbon ends up attached to that. Here it is. And now you say you want your carbonyl back. Well, it turns out just as amines in the form of imines are going to be capable of undergoing hydrolysis with just aqueous acid, likewise this. So all I have to do is a little bit of dilute acid, and I'll let you work out the mechanism. But the point is this becomes C double bond O, the water having supplied the carbonyl oxygen in your final result. But the end result is, if I started with this, and I wanted this, this enamine intermediate is an other approach that one can take. Think that makes sense to you? Well, I hope so. All right. So think of an enamine as I'm going to take something that has one alpha hydrogen environment. It can be an aldehyde, it can be a ketone, I don't care. But one alpha hydrogen environment only, because I don't want to have to choose where I'm going to have my alpha carbanion carbon. And I treat it with a secondary amine. And then I come along with whatever I want my disguised alpha carbanion to attack. And I run my reaction, then hydrolyze it at the end. And there you have a storic enamine synthesis. Okay? Here, what you're looking at is I've created my disguised carbanion, my so-called enamine. All right? And this time, I want my disguised carbanion to attack an acid halide, not an alkyl halide. As soon as I kick that out, I now have the attachment. And if I want, I can hydrolyze away the NR2 group and regenerate my secondary amine. And I now have a bigger and better carbon skeleton than I had before. Right? I'm going to perform this experiment, by the way, by looking at these slides in another room with another projector. We'll see if it's the fault of this projector. Okay, so questions so far? You good?
Question.
Please.
On hydrolysis, that's just, you're just putting acid in water? Or just,
Yeah, just aqueous acid. Think you'll be able to figure out the mechanism for how you end up with a C double bond O again? And you've regenerated your secondary amine? Okay, when we go over homework next week, this will be one of the things we address. All right, so let's see what else we have. Okay, so now we have something a little bit different, but not that much. Right, let's show you. Good. What I'm telling you is, if I have this kind of a system, what would you call that kind of a system?
Unsaturated?
Can you be a bit more specific? Using
It's-
Greek letters?
It's got space in its sigma bond. It's using, it's something about its bonds.
Question,
That
what
double bond
carbon
is-
is that relative to the carbonyl? Give me a Greek letter. Alpha, what's this one? What?
Beta.
So, this kind of system is called an alpha-beta unsaturated system. That's what it is. All right? Now, based on what we've been talking about, the stability of alpha carbanions that are generated next to a carbonyl pi system, think about it. If you come along with a nucleophile, that nucleophile can attack the beta carbon, and that would push a pair of pi electrons onto the alpha carbon. That would then be a carbanion that could delocalize that negative charge into the pi system of the C double bond O. In other words, this can form the so-called enolate species. Right? Now, once I have my alpha carbanion, I'm finished, and I can just add a little bit of acid, and that would put a proton on this alpha carbon, and the net result is that where I once had a C double bond C right next door to the carbonyl, now I don't have that anymore. I do have whatever this nucleophile was attached to the beta carbon. Right? And I'm showing you here at the bottom of the slide what some of these nucleophilic species might very well be. And they're the usual culprits in SN2 reactions, things like cyanide, ammonia, primary amines, even secondary amines. Notice what's conspicuously absent, what category amine,
Tertiary.
and the reason why it's absent, whereas secondary and primary and ammonia are all present, is what does it lack compared to any of the others?
Hydrogen.
No hydrogen, no reaction. Can't do anything. Okay. Still with me? Okay. So now, let's keep going here. What if my nucleophile is not any ordinary nucleophile, but it's something that either is an outright carbanion or thinks it's carbanion-like? So what are some examples of this? Well, you've already seen earlier this period that this is the alpha, where'd it go? This is the alpha carbanion of the malonic ester. That's that sandwich carbanion. This is the alpha carbanion of what could be acetoacetic ester. I'm just using any old general ester here. Here is what I was telling you earlier, this acylation product from the malonic ester or the beta keto ester approach. I can make a beta diketone. All of these are sandwich carbanions, classic. But also keep in mind that your Gilman reagent, the carbons directly attached to copper, the ones that are sharing electrons with copper atoms, carbon is winning the tug of war for those electrons, which means that for all intents and purposes, this reagent can be thought of as a disguised carbanion. And here you've already seen in the previous slides that enamines are disguised carbanion. Any and all of these, any and all, can attack where in these systems? Which carbon in an alpha-beta unsaturated system can an outright or a disguised carbanion attack? Which carbon? Alpha or beta? Beta. Okay. So we attack the beta carbons each time. Here's a question for you. Why is it possible to attack that beta carbon? Where's the pi system that's going to stabilize the alpha carbanion that's generated? Yeah, these arrows don't last very long. Yeah, it's a triple bond. So you're saying the triple bond can delocalize an alpha carbanion? No, it's a triple bond.
There's also a double bond.
Yes, and that's the double bond that's being attacked. Right? So in other words, a nitrile, despite what that seems to be showing you, that's a triple bond, and that is a pi system that also is capable of stabilizing alpha carbanions. Do you think a nitrile can stabilize it as well as a C double bond O? What do you think? Which one does the better job of stabilizing alpha carbanions, nitriles or carbonyls? Why? Bingo, because that's where the negative charge is going to end up. Oxygen is happier about it, but this gets away with it. And if, because of what you said, if oxygen is so happy stabilizing negative charge, doesn't get any better than nitro. Nitro like that. So you'd have negative charge on oxygen when it delocalizes that carbanion. So all of those are subject to this, and the chemist that investigated all of this and made this a major component of organic synthesis, this person's last name, not first name, last name was Michael, and this reaction, a type of conjugate addition, is named after him. But it's only when you actually are attacking the conjugated system with carbanions that are outright carbanions or think they are. One or the other. Okay. So let's go and see what else I have for you. There's not too much more. Oh boy. All right. This is work done by a chemist by the name of Robinson. And I think he did his work at Harvard when he was alive. And I think this was Nobel Prize winning work. He combined a pair of the reactions that we've been discussing. And let's show you. First of all, what kind of species is this that I'm pointing to while the arrow is still there? There it goes. What is that? It's an alpha, any kind of alpha carbanion. This is a sandwich alpha carbanion, and it is going to attack in Michael fashion. Notice which carbon, alpha or beta. Where'd that arrow go? That's something else we got to work on, getting that arrow to stay for more than a flash of time. So we attack the beta carbon. That gives us negative charge here, and eventually we allow that to pick up a hydrogen. So the point is, this is my Michael product. Still with me? Now, he could have just stopped it there and wouldn't have been anything that he then created, because Michael has already investigated this. But what he decided to do is now treat this Michael product with base. And what does this allow one to do? Well, if you look very carefully, you'll see that this is a set of alpha hydrogens. And if we're able to generate a new alpha carbanion, this alpha carbanion is perfectly situated to attack that carbonyl. And when it does, what have you just created? Something that nature loves. No. You're missing the major point. You've just created what? A what? I didn't hear. Say it again. What is special about this product? How big?
6.
Yeah. How many ways do you know of making 6-membered rings in organic chemistry? Bet you I can count them on the fingers of one hand, if even that number. Name a reaction whose only function in life is to create 6-membered rings. Say again?
Diels-Alder?
Diels-Alder, yeah. It's all you know up until this moment. Now you know another one.
Didn't you show us one the other night?
I did?
Yeah.
Yeah, you did.
And what was it called?
It was the Dickman.
Oh, yeah.
Yeah. The Diekman is another one. We're still on the fingers of one hand. So it's a very manageable number of reactions that allow you to make 6-membered rings. But 6-membered rings are very important. You'll see with some of the examples I give you why these are important. So the point is that this, as is indicated, is an aldol. Why is it an aldol? Because I'm using the alpha hydrogens on a carbon of a ketone to attack Notice, this is some kind of carbon group unspecified. Here's another carbon group. This is another ketone. Well, that's an aldol, right? And what does an aldol make? Answer, if this was my original carbonyl, this was the carbanion carbon, this is the beta hydroxy ketone product of an aldol. But because you've got this OH that's situated relative to one carbonyl and this other carbonyl, this OH realizes that if it's lost as water, you're going to be able to form a double bond there. This double bond is not only conjugated with which one? Which one of these carbonyls is it conjugated with? The bottom one or the top one? Just the bottom one. So in other words, carbonyl, alpha, beta. So it's an alpha-beta unsaturated system. And nature loves these things. So, in fact, you'd be hard-pressed to end up with the beta-hydroxy compound. This is almost as bad as having benzenes around that always want to form conjugated systems that are extended. This wants to do it too. All right? And this is called the Robinson annulation. And if you go looking up the word annulation, what do you think that means?
Happens regularly?
No.
Once a year.
Oh, you think it means annual? It has something to do with annual? This is a reaction that happens yearly? That's very good. Okay. No, afraid not. Answer is annulation literally means ring formation. Yeah. So anyhow, we have that. Let's see what's left over here, and then we have time to do a quick review. Okay, so here is a summary. If you have an alpha-beta unsaturated carbonyl system, and you come along with a nucleophile, the nucleophile, theoretically at least, has the option of attacking in the mode that we've been talking about, namely attack the beta carbon, put negative charge at the alpha carbon, and that's one way of building a carbon skeleton, or it can attack the carbonyl carbon directly, and here's your nucleophile, and here's an OH. And things like cyanide, which if this weren't there, would only make a combination cyano group attached to carbon with OH. Anybody know what kind of species that is? A geminal nitrile alcohol. What's its technical name? If you have OH and C triple bond N on the same carbon, you have a... Anybody? It's called a cyanohydrin. You'll have to spend the whole weekend looking this stuff over. Okay. So, the point is, normally, it would attack that without a second thought. As soon as you gave it the option of attacking the beta carbon of the extended pi system, it prefers to attack that. And that's what this is telling you. These electron-rich species always prefer to attack there, wipe out the double bond, put a hydrogen on that alpha carbon. You have some things like lithium aluminum hydride and alkyl lithiums or aryl lithiums. Some Grignards will prefer to attack the carbonyl carbon, but those are in the minority. Okay? Okay, so let's see if that's it. As far as spectroscopy of aldehydes and ketones, okay, this takes minimal time. In infrared, how do you know you're dealing with an aldehyde or a ketone? Where are you looking?
2200.
2200. I'm afraid not.
There's a spike at 1750.
A spike? How would you describe the signal you see at around 1700 for an aldehyde or a ketone relative to all the other signals in that spectrum? The carbonyl signal. How would you describe it in comparison to all the others? It's the what? We call that the strongest signal. Yeah. Yeah. It's the most intense. You can't miss it. Okay. So that's the story of the infrared, of aldehydes and ketones. For what it's worth, there are some less than impressive signals for aldehydes, but I'm not going to mention them. They're not worth mentioning. Is there anything special about aldehydes and ketones in proton NMR? Okay, aldehydes, okay. So ketones you'd never know from proton NMR, but an aldehyde you might have a chance. Because what makes an aldehyde? Answer that H directly attached to C double bond O. It has, if you're interested in remembering it, it has a characteristic region where this signal will show up. Anybody know what that happens to be, more or less? Ooh, very good. Okay. So I would say around delta 8 to 10. I'm being very liberal. 8 to 10 ppm. Okay. All right. In all aldehydes, no, I take that back. Okay, I'm not going to say it. All right. It's going to be roughly in that region. Okay. In carbon NMR, what's special about aldehydes and ketones? In carbon NMR, where is the carbon of the carbonyl of an aldehyde or a ketone going to be?
150.
No.
80.
Nope.
200.
Above or below?
Above.
That's right. In other words, the C double bond O signal, this carbon, for aldehydes and ketones, let's put it down, aldehydes and ketones, typically greater than 200 ppm. I'd let you get away with saying greater even than 180 ppm. Anything more downfield than 180 is telling you I'm an aldehyde or a ketone. So you ready? You've got a signal at 200. How do you know whether it's a ketone or an aldehyde? Yes, you do. Immediately, you know which one it has to be. They both come out in exactly the same place, but you know it's one or the other. How do you know? Okay?
The integration tells you?
No, there is no integration in carbon NMR. None.
The duplicity?
Say again? Hang on. Here is an aldehyde. Let's make one up. CH3. CH3. Here is a classic ketone. Like that. Right? This signal and this signal, exactly the same place in carbon NMR, 200. Yet I know which one of these two it has to be. How? Say again? No, I don't care about
One's a
the other
singlet,
signal.
one's a doublet.
What? Say again?
One's a singlet and the other's a doublet.
One carbon signal is a singlet, one carbon signal is a doublet. Which is which? The bottom one, this one? This carbon is a doublet? How many hydrogens do you see on this carbon? None. 0 plus 1 equals what lately? 1. Singlet for this. This is a singlet carbon signal. How many hydrogens do you see on the aldehyde? Plus 1 gives you what? Gives you a doublet. all aldehydes in the universe, with one exception, give you a doublet in the 200 ballpark. What's the one
Formaldehyde.
exception that doesn't? Formaldehyde. That one looks like this, like that. Hang on. And now the question is, how many peaks would that carbon signal beyond 200 ppm be? That would be the only triplet aldehyde carbonyl carbon signal. That's it. So that's the story for spectroscopy. Let me cut this off. Let me close this out. You think while I'm doing this. PowerPoint quit. Get rid of, clear the menu, and now let's shut her down. Shut down. And say yes. Okay. And now what I want to do in the waning minutes is I want you to benefit from an approach that one of my former students shared with us, and I've been using it ever since. And as fate would have it, I can't remember who it was that told me this, so be it. It'll be an anonymous former student. Okay, so let's do this. And I think you'll be impressed by this insight that she had. I think her last name, she came from either Ukraine or Belarus. Last name is Bagdasarova. Yeah. Anybody here have children? She's in pediatric dentistry currently. I don't know if she's making a living at it, but she's in it. Okay. So, she came up with this approach, so let me just show you. Let's say, by means of Robinson annulation, we made something like this. And a methyl group over here, and here. I think that's it. Okay, so that is the Robinson annulation product. And a question like this would be, here is this, and here is that. Okay? So you have two reactants, ultimately, by means of Robinson annulation, that can end up making this alpha-beta unsaturated diketo product. And things like this, with 6-membered rings and 5-membered rings fused to one another, this is already on the way to becoming, anybody know what the 4-ring system that's important in biological systems? Steroids, yeah, you betcha. Yeah. So you can see why this kind of work got the Nobel Prize. Okay, so how does one picture what this once was in a prior life? Now, if you recall the Robinson annulation slide, it starts off doing a Michael addition to an alpha-beta unsaturated carbonyl system. And then that product, the so-called Michael product, ends up doing a subsequent aldol condensation to make the 6-membered ring. Well, you can know all this in your head, but how practical it's going to be is pragmatic, debatable. So, you ready? Here's what she came up with. This is practically mindless. Watch. It's very impressive. She says, find the alpha beta carbons to the carbonyl that was right there. Before this double bond became a double bond, what do you think it was in a prior life? So, we'll do more of these next week too. So, what I'm going to do is the following. Your textbook may use this approach. I don't know whether you've seen it. Have you seen this kind of hollow arrow in the textbook anywhere?
Retro.
Yeah, you look. It's called retrosensitive. I'm not a big fan of it, but I'll use it now. What I'm trying to do is show you where this came from. So what I'm doing mentally is I'm saying before there was an alpha beta unsaturated system, how did that double bond form? What was lost to create it? Wrong-o. An OH along with? OH along with? H. Namely, what'd you lose? Water. Yeah. So watch this. So the H was at which carbon? The OH was at which other carbon? In other words, I'm asking, the OH was at the alpha carbon relative to this, or the beta carbon? Beta. That would be a good guess. So here we go. All right? And here we have H and H. So she says, picture that. Now, she says, how was this formed? Well, what is this? This is a beta hydroxy ketone. Beta hydroxy ketones are the result of what name brand reaction? Nope. Claisen makes beta keto esters. This is neither I can't say it, an ester or a keto. So, which reaction makes this? Beta hydroxy ketones or aldehydes? Aldol. So, how did the aldol reaction happen? Answer, before this bond was made, what was this carbon? Before this bond was made, what was that carbon? Yeah, that's way before. Right.
Oh, carbon.
A carbanion. Okay. No, you're right, but not yet. Okay. So you ready? What we have here is this carbon, negative charge, that's my alpha carbanion. And before this was an OH, what was this carbon? Better known as carbonyl for the rest of us. Right. Okay.
I don't know how to speak English.
There we go. Still with me? And then before, now it's your turn. And before this was a carbanion, it was a methyl. There we go. So watch this. So here we have CH3. Okay? So that was the last step in the Robinson annulation, the aldol. But before the aldol was a Michael addition. What's a Michael addition? A Michael addition is a sandwich carbanion attacking the beta carbon of an alpha beta unsaturated system. So where can you picture a bond being made by a Michael addition? Or, put another way, where in a prior life can you see an alpha carbanion sandwich?
Attach the top.
Is this a carbon that could be sandwiched? What are we pointing to?
Well, no. The one attached to the methyl.
Ha-ha! So you're saying this in a prior life could have been my sandwich carbanion. Well, hell yeah. Well, if this carbon was the one that was the sandwich carbanion, what did it attack? It attacked this one, right? In other words, this bond wasn't always there. And in fact, this, here's CH2, here's that. So here is one of our reactants. And here, all you have to do is just put back the hydrogen. That's your other material. Isn't that cute? I think that's cute. Because it works on all kinds of strange looking stuff. Haven't found any flaw in this at all. So on that note, I'm going to leave you unimpressed and hope that you'll come back next week and that the weather permits us to. And we'll do a number more, and then you'll see how nice this is once you get the hang of it. Yeah. So,
Oh, I already shipped you.
I already
that.
showed it.
So basically what it is we have an installation
Yeah.
here.
I don't have a right clip.
It's just at the far right.
Oh, yeah.
Right click,
What are you doing? Pointer option. Oh.
arrow option.